In this video, we're going to be talking about the Pythagorean Theorem, in particular, the proof. Why does it work? How does it work? So before we get started, here are a few things that you need to know. You need to make sure that you're comfortable working with the formulas for the area of a square and the area of a triangle. You also need to make sure that you are comfortable with the concept of polynomials. It's kind of light on polynomials, but still polynomials nonetheless. So let's begin. So I've drawn here just a small little diagram. It's a square. And if you remember the Pythagorean theorem and you remember what it says that a squared plus b squared is equal to c squared. Now this is relating the sides of a right triangle together. So let me just draw a quick little right triangle here for us, where a and b are going to be the lengths of the sides of the two shorter segments, and c is going to be the length of the hypotenuse, that being the side that is opposite the right angle. Now I've taken this basic shape and I have kind of fit this into a square. So we have a square that has side lengths that are a plus b on each side. You can see that as we go around here, each side is made up of a plus b. And you've got each corner. And so you can see how we are forming our right triangles. So you have A and B being the legs of the right triangle, and here is C being the hypotenuse. And it is a right triangle because we put that inside the corner of the square. And this is going to be repeated for all four corners here. And you may be wondering, how in the world does this prove the Pythagorean theorem? I mean, I think a lot of us know the theorem from geometry, from algebra, and it's just one of those things that we have just come to accept. It just is what it is, right? Well, here's what I'm going to show. I want to take the area that is inside each of those triangles, and I want to see how does the combined area of those four triangles, these are four exactly the same triangles because they're all, A, B with the same hypotenuse. I want to see how does that area compare to the area that is inside the square. Because if you look inside there, we basically form a square with side C. At least that's what it seems to be, right? So let me just clean up a little bit here. We're going to come back to you. Yes, I know. You're gone, but never forgotten. All right. Well, if you look at the big overall square, remember that the area for a square is going to be s squared. And for us, our side length is going to be the combination of a and b. So that means for this formula, it's going to be a plus b, the quantity squared. All right. Well, if we remember a little bit about our algebra and polynomials, we know that this guy multiplies out to give us something very, very special. So this is one of those nice formulas from algebra. The a plus b quantity squared is equal to a squared plus 2ab plus b squared. And if you are having a hard time believing me on that, what I recommend you do is that you take a plus b times a plus b and FOIL that out. And what you're going to find is that it is exactly what we have right here. It's just that we see this so often that we have this formula because there's no sense in foiling out this formula every single time. We just know it, and we use it, and we go on. All right, so that is going to be the area of the big overall square. But what I want is I want the area of that blue square in the center. So I think it's pretty clear that since we have a square inside here, that the area for this blue guy is going to be c squared because that's going to be side squared. And that's the area of that blue piece. All right, but let's do a little bit of algebra here with geometry. In order to end up with just that blue shaded region on the inside, we need to take the entire area of the square, which we have right here, and we need to subtract all of those little triangles. Now, you will remember that the area for a triangle is 1/2 times the base times the height. So what does that mean for us? Well, for each of these triangles, we have 1/2. The base, doesn't really matter what you say here, is b, and the height here is a. And what I'm doing is I'm looking specifically at this guy right here. Base is b, the height is a, so the area is going to be 1/2 that. But how many triangles do we have? We've got 4, right? So let's put this guy right here with the big area, and let's see how this works out. So for the area of the blue square, it's going to be the area of, I'm just going to do it like this, area of the big square minus 4 times the area of each of those triangles that we have. Okay? So that means that we would have a squared plus 2ab plus b squared, because that would be the area of the big square. So let's kind of color code this so it's a little bit easier to see. All right, so the area of the big square is that guy right there, right? Minus 4 times the area of those little triangles. And each triangle was, as we found out in the last step, 1/2 b times a. And we can just write those guys right next to each other. It indicates multiplication. So we have, oh, just kidding, I pressed the wrong thing. So the area of the triangle is 1/2 base times, or b times a. And let's simplify this. So we really just need to keep writing down the a squared plus 2ab plus b squared minus, now when you do the multiplication here, 4 times 1/2, well, 4 halves just gives us 2. And even though I have b times a, they're connected through multiplication, so I can just as easily rewrite that as a times b. And wouldn't you know it, you have a plus 2ab and a minus 2ab. So these guys reduce, giving us just a squared plus b squared. But remember what all of this was for. All of this right here was to give us the area of the inner square. But if we scroll back up here, we see that we already know the area of the inner square to be c squared, because it's a square, and the area of a square is side times side, in this case c times c, that gives us c squared. So that means that all of this is equal to c squared. Thus we've shown that a squared plus b squared actually does equal c squared. It's kind of crazy, right? Something that we just assumed was true because the teachers told us it was true. We've now been able to prove through a bit of geometry with pictures with right triangles, and we show that it works. I think that's really cool. You get to see it, and it just, to me, it just makes a lot of sense. Well, I would say if you like this video, hit like or subscribe or bells, and shout outs and whatever, but what do I know? I'm just a guy who's on Twitter. So thanks for watching.